What's up, everyone? Welcome back to the Golang data structure series. This time, we're going to get a little bit more complicated than we did so far. So, in the last videos, we covered linked lists, doubly linked lists, stacks, and queues. So far, we have done a lot of the linear data structures that can be built. So, this time, we'll be creating a tree data structure, and I'm specifically talking about a binary tree. And this isn't a binary search tree, it's just a regular binary tree. And if you don't know what a binary search tree is, don't worry about it. We'll cover it in the next video. So in this video, we'll be covering binary trees. So let's just create a package real quick. So let's talk about what a binary tree is. Just like a linked list, which had nodes, a bunch of nodes, and each node had a value, a next pointer, a previous pointer. This is a doubly linked list, by the way. Uh, just like this structure, we can create a similar connected structure which would look something like a tree, which would have a hierarchy. We would have a root node which has a bunch of child nodes. We'll understand it as we code this thing out. So we'll just call this a binary tree node. We would have a left child and a right child, which are both binary tree nodes. And then we would have a binary tree, which would be a struct. We would have a root node, which would also be a binary tree node. So this is what the data structure would look like visually. This is the root node, and we would start creating child nodes for each node. And the way we would fill up this structure would just be that if one level has been filled up, then we just move on to the next level. And once this is filled up, then we move on to this level. So the next item that we would the next node which would be created for three as the left node, and then the right node, and then we would move on to creating nodes for five, and so on. So we would go level by level insertion. That's the way we would insert items into this structure. So let's just start by creating some functions. So we would have a new binary tree node function, which in this case we would take a value, which would be an int. So we'll be accepting nil values to be inserted into the tree just to make it a bit more flexible. So we would return a new binary tree node where the value would be the val that was provided, and the left child would just be nil, and the right child would also be. We'll need to provide this as the return type, and we'll need to dereference the value before assigning it to the value. Awesome. So we need that function. We'll also need the function that creates a new binary tree. So let's just write that real quick. And we will be providing a value for the root node that we'll be creating. So the binary tree that we will be returning, we will just be creating a new binary tree with just the root node. And the root node would just call the new binary tree node function with the provided value. Oops, I almost forgot. We'll need to return a reference to the new node that was created so that we can have it as a pointer because the root is a pointer to a node. So that's the reason. Awesome. So we have ways to now create new nodes and a new binary tree. Now let's figure out how we can insert into the binary tree. So let's just call it insert. We call it insert binary tree. And now, as I mentioned, the way we insert into a binary tree is we fill up layers one by one and we go to the next layer whenever a layer fills up. And the way to do that is we use a queue data structure uh, to like push each node that we encounter. So let's say we encounter this node, we push it onto the queue, and then we check if it has the left child and the right child. If it does, then we push those onto the queue, and then we pop the next item in the queue, which would be now two. And we would check if it has a left child and a right child. If it does, then we push those into the queue. And then we pop the next item out of the queue, which would be three. And we check if it has a left child and a right child. If it does, then we push those onto the queue. And we see that in this case, there are no left child. This node does not have a left child. So this is where we need to create the new child. So we'll first need to create a queue, and this is where we will take advantage of the queue that we have implemented in the previous video. If you haven't watched that yet, go check it out. I'll leave a link to it in the description, and that should be enough. So we'll create a queue. We'll just create a regular vector queue for now because that's the most easiest way to do this. So we'll have a vec queue. If we have a new method here, we did not, so we'll just create a new one real quick. So I made this new function for our queue just so it's easier to create a new queue in our binary tree implementation. And I have had to uh, make this data field public. And the other modification that I'm going to make is instead of just storing integers here, I'm going to store an interface. And because of this, I'll be able to store nodes inside this queue, and this will come in handy in just a sec. I'll just modify all the places where we've coded up the interface. Another thing that I'm going to do is check size. This will be a bool. So whenever this is false, we will not be checking if the queue is full, or we will still check if it's empty, but we will not check if it's full because in that case, we're not setting any size limits for our queue. So that's another modification that I've made. So now that I've made all the places where we were setting data as a slice of ints, I've made a slice of interface, and I've added the check where we only check for the max size to be hit if we have the check size set to true. So now we can use the queue vec in our binary tree implementation. So first we'll need to instantiate the queue, uh, and I'll just call the new queue vec function there, in which I will make the interface, and I will have like a zero max size, and I will pass check size as false. So now that we've created this queue, we can now use this for our binary tree implementation. So to do this, we will need to run a loop which will run as long as the queue uh, has any items in it. So I'll just do this. So that. So as long as there are any items in the queue, run this loop. And right now, this will immediately exit the loop because we don't have any items in the queue to begin with. So I'm going to enqueue the current binary tree's root into the queue. So the way to do that would be t.root. Now there is one item in our queue. So the loop will be run. So inside this loop, we will keep track of what the current node is. So as I've said, we go level by level and we consider each node if it has a left node or a right node. So we start from our root node, we pick this out of the queue, and we check if this item has a left child and a right child. If any of those is not present, we first check if it has a left child. If it does, then we move to check if it has a right child. If it doesn't have a left child, then we just add the new element to its left child. If it does, then we check if it has a right child. If it doesn't, then we insert the new element there, and so on. We then move to the next level. So our current item in this case would be that. And we implemented our dvec such that it will return whatever was dequeued out of our vector. So the next step would be to check if it has a left node. And before we do that, we need to perform type assertion on the current while we. perform the dvec because uh, the compiler doesn't know what kind of item the dvec is returning because it's returning an interface, but it doesn't know if it will have a left child or not. So we need to specify this by converting uh, whatever is returned by this, we're converting it into the type of the binary tree node. Okay, so if it is nil, then we just create a new left child, which would be, we'll need to call the new binary tree node. So we do that, we pass the value which was passed, right? So it's directly returning a pointer, so we don't need to dereference it. So once we have inserted the new node into the left child, we would just return out of the function. And if this is not the case, if the left child is present for the current node, then we would enqueue the left child onto into the queue that we are maintaining. So this is what we could do with the right child as well. So we would check if the right child is present. If it isn't, then we just set the right child as whatever the new node we've created. If it is present, then we just enqueue that right child. So this is our insert method of the binary tree. Let's just take a quick example and visually understand what's going on here. So if this is the queue that we are keeping track of, and if this is the binary tree that we are trying to insert into, let's say that we are trying to insert the element 12 into this binary tree, then we would first take our root node, we would enqueue it into the queue. So we would have this. Since there are elements in the queue, we would enter this loop and we would pop that element. We would check if one dot left node is present. In this case, it is. So we would add the left node to the queue. So we now have two in our. Now we check if it has a right node. So we would check one dot right. It does have a right node. So we enqueue that as well into the queue. We go on to the next iteration. We pop another element out of the queue, which would be 2 in this case. We would check if it has a left node. In this case, it does. So we push that onto the queue. Now we check if it has a right node. It does. So we add that onto the queue. Now we have finished checking both left and right. So we move on with the loop. Now we get to the node 3. We check if this node has a left node. It doesn't. So we assign current dot left child the newly created node, which would be 12, and we would return out of the loop. And we have successfully inserted an item onto the tree. So we're essentially inserting in level order where we fill up each layer before moving on to the next layer. Make sense? So we can create a new test function here, which would be called test binary tree. And as we've done this previously, this isn't technically a test. We'll just be creating a new tree and inserting it into it a bunch of times and printing it out on each iteration and just visually testing it. Let's just start by creating a new binary tree, and we would use our new binary tree method, and we can just insert a root value. We need to have the root value here. Let's just have it as 1. And now to easily perform a bunch of inserts, we can have an items array here, which would be an int array. We would have that, and would loop through the whole all the items, and we would perform a bunch of inserts. This is the root of the tree, and we're inserting all of these items onto the tree. So to better visualize this, we'll need to have a binary tree dot print binary tree method, and we're going to implement that now. So this will be a new instance method. We'll call it a print binary tree, So even while printing, we will need to perform a similar kind of operation that we did while we were inserting onto the tree. So we can just copy over whatever we had and we can modify this now. So we will be looking through all of the items just like that. So we'll be creating a queue, we will add a root into it. We would first get the size of the level that we have. So the way we would do that is just get the length of the queue data and for let's say I0 I less than the level size I plus plus. Level size indicates how many items there are on the current level of the tree. So we loop through the number of items there are in the current level. We get the current item from the queue, which would just be a queue.dvec. dvec. We would type convert this into a binary tree node. Now we can print this the current item, current dot value, and if the current dot left child is not nil, then we push that onto the queue and vec current dot left child, and we will do the same thing with the right child, queue dot nvec current dot right child. And once we have finished printing out all the items in the current level, we would just print out a new line. And I messed that up here. So we want to do a print f here because we want it to look like a tree after we are done with the whole printing function. And once we have printed out all the items at the current level, we just perform a print line, which will just create an empty line. So let's just try to run this. We need to call this function from the main and run it. It's a bit difficult to understand what's going on, but what we want is happening. We are inserting all the items. Let me just try to make this a bit easier to understand. So once we have inserted the root item, I'm going to print. And at the end of our print function, I'm just going to have like a bunch of new lines at the end of the print function. Now let's try to call it again. So as you can see, we first created our root node. Then we inserted one item for our tree. Then we inserted another item. So one is the root node, two is the left child, three is the right child. Then we inserted four, and four is the left child of two. Five is the right child of two. Six is the left child of three. Seven is the right child of three. And if we were to insert one more item, then we would see that it would go on to the next level. Makes sense. So our insertion into the tree is working correctly as we want it to. Now we can move on to deletion. So we're just going to continue deletion in the next video because there are a bunch of different ways we can implement deletion. So I'm going to discuss all of them in the next video. So stay tuned for that. Thanks for watching. I'll see you in the next video.